Good morning, good afternoon, everyone. We are going to discuss about C13 NMRs today. C13 NMR spectroscopy. You have an idea about spectroscopy. I mean, you have studied some of the spectroscopic techniques in first year. What is spectroscopy? Actually, what is the importance of spectroscopy? Spectroscopy is a tool, actually, to study the structures of various organic molecules. Not only organic molecules, we have spectroscopic techniques to study inorganic molecules also, but we are going to study about organic spectroscopy in this discussion. Okay, and the definition of spectroscopy, you know, what is the definition of spectroscopy? How many types of spectroscopic techniques are there? Just to name few, like ultraviolet spectroscopy, infrared spectroscopy, NMR, proton NMR spectroscopy, mass spectroscopy, and so many other techniques like C13 NMR spectroscopy, two-dimensional NMR, etc. All these are very useful to study the structures of the molecules, known or unknown molecules. Okay, and in this discussion, today's discussion, I am going to discuss about C13 NMR spectroscopy. So, C13 NMR spectroscopy today I am going to discuss about C13 NMR spectroscopy. So, what is spectroscopy? Let us just revise whatever you have learned in your first year. Spectroscopy is the study of interaction of matter with electromagnetic radiation. And different type of spectroscopic techniques deal with different parts of electromagnetic radiation. For example, EMR, electromagnetic radiation, has got different wavelengths and frequencies, you all know. And actually these different frequencies interact with matter in different ways to give specific information about the molecular structure. For example, interaction of matter with IR part of electromagnetic radiation gives an idea about various functional groups present in the molecule by way of stretching frequencies. Okay. For example, you have carbonyl group in the molecule. You get carbonyl absorption in the IR part of the radiation. So you'll be knowing about various functions present in the molecule from the study of IR spectrum. Similarly, interaction of matter with UV radiation gives information about electronic excitations. You will know about whether you have aromatic benzenoid skeleton present in the molecule or extended conjugation is there, what are the chromophoric groups present, etc. NMR. What is NMR? In NMR, magnetic nuclei that are present in the molecules interact with the NMR part of the electromagnetic radiation. So interaction of matter with the NMR part of electromagnetic radiation gives information about the type of magnetic nuclei present and their chemical environment in the structure. For example, let us just, because you have studied about proton NMR, I'll just give you simply revise whatever you have learned in proton NMR. From proton NMR, what is that you know? Sorry. What is that you know? From the number of signals, you get information regarding the types of different protons present in the molecule. And from the chemical shifts, you get the information regarding the chemical and magnetic environment of the molecule. And from the integration curves, you get information regarding the number of protons in each set. And from spin-spin coupling patterns, you know what are the neighboring protons present in the molecule. Okay. So this already you have learned. I'm not going into details of it. So you know pretty well that what is NMR? Nuclei of certain elements. For example, C13, H1, F19, P31, and various other elements are there which are magnetic. So they are magnetic. So they are magnetic means they behave as small magnets. Okay. So like any other magnet, in the presence of a strong external magnetic field, these nuclear magnets align with the applied field or opposite with the, this is alignment, means in line with the applied magnetic field. And this is opposite in line with the applied magnetic field. So when they are aligned with the magnetic field, their energy is low. And when they are opposite to the applied magnetic field, then the energy is high. Actually, in the absence of, what is the need of magnetic field here? In the absence of applied magnetic field, the magnetic nuclei present in the molecule are randomly oriented. They are not oriented either, systematically. They are randomly oriented, so the net magnetic field will not be there. Whereas in the presence of applied magnetic field, they align either with the applied magnetic field or opposite with the applied magnetic field. So that means two energy states are generated here. One is lower energy state and the other is higher energy state. So when they are in line with the applied magnetic field, that is low energy state for the nuclei. So there will be some net magnetic moment. And there are nuclei that are aligned opposite to the applied magnetic field. So that means they have a little bit higher energy. So the nuclear energy states, these spin states, is that, I mean, they have different energies. That means there is energy difference created, delta E. So that delta E is actually that part that is very small, and that is the reason why nuclei can absorb, magnetic nuclei can absorb very less energetic part of electromagnetic radiation, that is Nmr part of the electromagnetic radiation, radio frequency range, means longer wavelength, I mean very low energy radiation. And so that is I mean, basically any magnetic nuclei, let us just revise, any magnetic nuclei, when in the absence of applied magnetic field, what happens? In the absence of applied magnetic field, the magnetic nuclei, the tiny magnets, different, so many molecules will be there, different nuclei. I mean, the nuclei, magnetic nuclei that are present in the molecules are randomly oriented. When magnetic field is applied, what happens? They are either aligned with the applied magnetic field or opposite in line with the applied magnetic field. So, as I told you, we have different magnetic nuclei. Proton is magnetic, C13 is magnetic, and there are some other nuclei that are magnetic. So, as I told you, we are going to discuss about little bit about C13 NMR today. Okay. So, what is C13 NMR? What is its significance? How it is going to be useful for an organic chemist? So, as you all know, carbon is a center of interest, is it not? Without carbon, there is no organic chemistry at all. So, carbon is the center of interest in organic chemistry. So, from C13 NMR, we can directly observe the carbon skeleton. Whereas from proton NMR, what is that you observe? You observe the structure, but indirectly. You will be observing protons and which are attached to carbon. So, from that, so indirect framework will be knowing. Not direct framework. For example, if you take ethanol, CH3 protons you observe, CH2 protons you observe, and OH proton you observe. And from their multiplicity patterns, you will know that CH3 is attached to CH2 and CH2 in turn is attached to OH. So from the multiplicity and chemical shifts, we will be able to know that is a CH3, CH2, OH molecule. But whereas in C13 NMR, you will be knowing directly, you will be directly observing CH3 carbon, not indirectly. Directly, you will be observing CH3 carbon and CH2 carbon also. So, you know, many natural products, they are they have very complex structures, and the proton NMRs of those natural products will be very complex. Let me check. Hello? Am I audible?
Yes.
Am I audible? Is it clear?
Yes, ma'am, it is clear only.
Okay. Yeah. Is it clear now? Can you see the screen?
Yes, ma'am.
Yes,
Oh.
yes.
Oh. So the center of interest in organic chemistry is carbon. As I told you, without carbon, there is no organic chemistry. And you know, many natural products contain more carbons than hydrogens. Hydrogens are very less, and they give very complex proton NMR spectra. For example, if you take cholesterol, it just look cholesterol proton NMR spectrum just looks like a multiplet of peaks. Without you cannot interpret anything out of it. So like that, not only cholesterol, many other steroids and many other natural products, they have got very complex structures. They have more carbons than hydrogens sometimes. And those hydrogens also give proton NMR, very complex proton NMR spectra. So that means you will not be able to get anything, you will not be able to interpret anything from just proton NMR spectrum. Though proton NMR is very good for interpretation of many molecules, there are some molecules which you cannot elucidate the structures just by looking at the proton NMR spectrum. So that is, there is the need for C13 NMR. Okay. So C13 NMR will give you the backbone of that organic molecule. So directly, because you will be getting direct carbon framework, so we will be getting a simplified spectrum just from, and we'll know the carbons, how many carbons are present, how they are attached, how they are bonded to, etc., etc. So that's the reason why sometimes C13 NMR will come into your help when you are especially studying some complex natural products which have got less number of protons and also closely spaced signals, like closer chemical shift ranges, where you will get complex NMR spectra. That's the reason that you will not be able to get relevant information, useful information just by studying proton NMR spectra. See, that's what I have given you here. Just proton NMR is not enough to illustrate the structures of such compounds. Okay, so in that case, carbon-13 NMR is going to give you a lot of information regarding the bonding state of the carbon and regarding the number of carbons, type of carbons, etc. Okay, so that's the reason why that is the significance of C13 NMR. So how C13 NMR is obtained? You know, C13 NMR, when we say C13 NMR, we are talking about the carbon nucleus. So why we say C13? Why not just carbon NMR? Why? Because carbon, you know, the natural abundance of carbon 12. Carbon has got two isotopes, carbon 12 and carbon 13. And carbon 12 is non-magnetic. So its I, that is, its I value is 0. So when I is 0, it is non-magnetic. When I is positive, then only a nucleus is positive. That you must have learned in proton NMR, is it not? So carbon 12, I is 0. Whereas for carbon 13, I is half, 1 by 2. And what is the I of proton? It is also 1 by 2. What is the I of F19? That is also 1 by 2. That's spin. Okay, spin value. So since C13 has got I positive, that is 1 by 2, it is magnetic. So that's the reason why carbon 12 cannot be absorbed by NMR techniques, and carbon 13, since its I value is 1 by 2, it can be absorbed by NMR spectroscopy. That is the reason why we call it C13 NMR, not just carbon NMR. Okay, so carbon NMR means it is carbon 13 NMR. You know, sometimes we say carbon NMR also. That itself means it is carbon 13 NMR. Okay, and okay, fine. Carbon 13 is magnetic. It can give you the NMR spectrum. But the problem is its abundance is only 1.1%. So and its magnetic moment also is very less than proton, almost 1/4 of the proton. So therefore, its abundance is less and its sensitivity is less than proton. That is the reason why its total overall sensitivity is only 1 by 66,000 as compared to proton. That means the signal intensity, when you compare to proton, is very, very, very less. So that's the reason why when you want to record proton NMR, small samples are enough. The 5 mg, 10 mg is enough. Whereas if you want to record C13 NMR, you need a little bit more sample. But however, we have now advanced NMR, advanced instruments wherein you can get a good NMR, C13 NMR spectrum also from less sample. But even otherwise, even then, proton NMR is going to be more sensitive. It requires very small sample as compared to C13 NMR. So the reason is its abundance is very less as compared, because proton NMR hydrogen is not 1.1%. It's almost 99, more than 99%. Okay, almost 100%, near to 100%. Whereas carbon-13 has got only 1.1%. And which is magnetic, because and for getting NMR spectrum, the nucleus should be magnetic. If it is not magnetic, you cannot get an NMR spectrum. Okay, so that's the reason why carbon-13 NMR has got very, very low sensitivity. So since the sensitivity is low, CW technique, this continuous wave method, is not used normally because it takes days, I mean sometimes weeks, to record one spectrum. Continuous wave method, you have got two methods, continuous wave technique and PFT, pulsed Fourier transformation method, to record NMR spectrum. We will discuss later about this. But continuous wave method is continuously each and every absorption is recorded, and that sometimes if the sample is less, sometimes it may take 1 week, 10 days also to record just one spectrum. Okay, so that's a reason why CW technique is not used normally, especially when you are recording C13 NMR spectrum. Of course, even proton NMR also nowadays they are using FT NMR only. Okay. Then, what are the advantages of C13 NMR? Advantages are many. As I told you, direct carbon skeleton can be observed. Direct carbon framework can be observed, and another very important advantage here is the chemical shift range is very wide. 0 to 240 ppm, whereas proton NMR it just is 0 to 10 and for general molecules, and 0 to 14, up to 14 or 16 for enols, etc. But whereas carbon signals, they have got chemical shifts, a wide range of chemical shifts. That is the reason why each and every carbon will be observed separately, and you'll be getting different signals for different carbons present in the molecule. So that's the reason why you will be able to, the spectrum is simplified, and you will be able to get direct carbon framework. You will be able to know the structure of the molecule very easily. Okay, and what is the other advantage? The chemical shift differences also is more as compared to PMR. In PMR, since the range is very small, almost for all organic molecules, protons, the range is between 0 and 12 or 0 to 14 ppm. 0 to 12 only, we can say 0 to 14 and 16 only for enols, and only for specific protons we get the chemical shift in that range. But up to 0 to 10 normal, 0 to 12 like aldehydes, carboxylic acid, etc. like that, but not more than that. So in that only, all the protons, that wide, many organic molecules have got different type of proteins, and their chemical shifts fall in that small range only. So that's the reason why it's most of the time they are very, I mean, there will be overlapping, and complex spectra you will be getting, and multiplicity signal spin coupling further complicates the problem. So most of the time we'll be getting second order spectra, especially for complex molecules. Okay, so that problem is not to be seen here. So that can be avoided here, because the chemical among various carbons is more. So that's the reason why each and every carbon appears separately. So therefore overlapping is minimum. And another very important advantage is you can observe non-protonic functional groups also here. Whereas in proton NMR, you cannot observe non-protonic functional groups. You can observe non-protonic functional groups here. And What are the non-protonic functional groups? For example, cyano, carbonyl group, carbolic acid group, ester group, and disubstituted alkyne carbons, tetrasubstituted alkenes, hexasubstituted benzenes. In natural products contain sometimes benzene ring with fully all 6 carbons substituted. So, in such cases also, since hydrogens are not essential here, whereas in proton NMR you need a hydrogen atom to record the spectrum. So that's here you don't need a hydrogen. Just carbon is enough, and because it is a backbone, it can directly give you the signal, and you can directly observe all these functional groups also. So it's possible to identify the carbon backbone structure, and even mixers also can be identified easily because mixers contain, again same, because the spectrum is simplified. Different carbons will give you different spectra, even if in mixers chemical shifts are different. Therefore, you'll be getting you'll be getting simplified spectra, which you can identify easily the mixers also. So we will be learning about it with the suitable examples later. Okay, and principle. This principle also same as PMR. What is the principle of PMR? As I told you, when in the absence of applied magnetic field, magnetic nuclei, protons are randomly oriented. In the presence of applied, this is P0 is applied magnetic field, this is nuclear magnet. In the presence of applied magnetic field, I told you, they can have 2 orientations. One is in line with the applied magnetic field, the other is opposite in line with the applied magnetic field. So they will align, and another thing also they will do, they'll be spinning as it is. The protons are spinning already. That is their character. And that spinning magnetic nucleus, they will undergo a characteristic moment precession, we call it. You must have seen the top, top moving in the Earth's magnetic field. The top, when it is about to fall, it will be like this only. You can just observe it. Okay, this is also a tiny magnet. It also rotates around the axis of the applied magnetic field like this. Okay, so this is known as precession. Okay, in the presence of applied magnetic field, this tiny magnet, what happens to it? It will rotate around the axis of the applied magnetic field, which we call precession. Okay, axis of precession. This is axis of precession. So it has got a particular frequency. What is the axis of spin? This is the axis of spin. This is spinning nucleus, a tiny bar. It just behaves like a tiny bar magnet. Okay, it is spinning. It is spinning as well as precessing. Spinning is around its own. Like you can take the examples. Like when you go to temple, revolving about. If you do revolve around yourself, arc projection we call it. Okay, if you do that, that is spinning. And if you go around the temple, that is precession. Okay, when you are moving, rotate. Revolving. Moving. Arc projection. If you are doing yourself, and if you are around your own axis, that is spinning. And going round the guard in the temple is precession. So each nucleus has got a different precessional frequency. Okay, that precessional frequency, this precision, it can be very fast, it can be slow also. It has got different precessional frequency. Actually, our NMR, when we get different signals based on these precessional frequencies only. Okay, so what let us just revise. In the presence of applied magnet, in the absence of applied magnetic field, what is happening? All magnetic nuclei are randomly oriented. Whereas in the presence of applied magnetic field, what is happening? Some of them are aligned with the applied magnetic field, and some of them are aligned opposite with the, they're positioned themselves opposite to the applied magnetic field. So that thereby creating two energy states. So some nuclei will be precessing will be precessing in line with the applied magnetic field. Some will be opposite in line with the applied magnetic field. So there will be small excess of nuclei, small excess only, very small excess, 1 in 1 million. For example, 1 million, 1 in ground state, just 1 million will be in upper state, higher energy state. So that means how many nuclei are contributing to the magnetic moment of this? Magnetic moment here? Only 1. If you have 2 million 1 molecules, 1 million 1 will be in lower energy. Just as an example, I am taking 2 in 2 million 1. If you have 1 million, approximately 1 million 1 nuclei in lower energy state, and 1 million will be in upper energy state. So the magnetic moments of these 1 million nuclei will get cancelled. So only 1 nucleus that is in extra, more in lower energy state, that will contribute to the excitation. Okay, so that's the reason why it's sensitive. And not just million molecules will be there, many millions will be there. That's the reason why overall there will be slight magnetic moment when, in the applied magnetic field. Okay, so I told you, nuclei are spinning around their own axis, Atma projection, and they are precessing, means going around the magnetic field. Okay, going down the applied magnetic, that axis of the applied magnetic field. Okay, so that they have got that precision has got a frequency which we call precisional frequency. So these precisional frequencies vary. I'm just giving you as an example, few precisional frequencies of carbon here. In the presence of applied magnetic, this is dependent on the applied magnetic field. If the applied magnetic field strength is more, precisional frequency is more. If the applied magnetic, please, there is a typographical mistake. B0 is not there. This is applied magnetic field. B0 is applied magnetic field. There is no B0 here. It's only precisional frequency. Okay. So in the presence of applied magnetic field, the nuclei presses. They have got precisional frequencies. So how much precisional frequency they will have? It depends on the magnetic moment, overall magnetic moment of the nuclei. And also overall applied magnetic field that is applied to this sample. Okay. For example, if it is 1.4 Tesla, carbon has got 15 megahertz, not hertz, 15 megahertz. This is also a print mistake. 1.4 Tesla, 15 megahertz. Megahertz precisional frequency it has got. What is the precisional frequency of proton here? You have studied in your first year. What is the precisional frequency of proton at 1.4 Tesla? It is 60 megahertz. See, almost 4 times than the carbon. 1.4 Tesla, 15 hertz, whereas proton, it is 60 megahertz. Similarly, 1.9 Tesla, 20 megahertz. And similarly, this is carbon precisional frequencies. And 2.3 Tesla, 25.2 megahertz. And this is 100 megahertz for proton number. That means almost 4 times, because the magnetic field of the proton almost 4 times in the carbon. And in other words, carbon magnetic moment is 1/4 of the proton. Proton has got more magnetic moment than the carbon. So that is the reason why precisional frequencies also change. That is, and here I can ask you a question. See, for example, we are doing the same, we are taking the same instrument, same radio frequencies will be there, magnetic field will be there. But, and organic molecules have got both carbon and hydrogen. But when you are recording hydrogen spectra, that is proton NMR spectra, you will not be saying carbon spectrum. When you are recording carbon spectra, you will not be saying proton NMR spectra, proton signals. Why? Just try to read, try to understand, and tell me the answer later. If you don't get the answer, I'll explain in the later classes. Okay. So So what is that we have seen? Carbon 13, a magnetic nucleus, when placed in applied magnetic field, has got carbon nucleus has got different precisional frequencies. These are the precision frequencies of TMS. Okay, that is the reference used. 1.4 Tesla, 15 megahertz. 1.9 Tesla, 20 megahertz. 2.3 Tesla, 25.2 megahertz. So Nmr equation. What is Nmr equation? This also you have studied. This is the fundamental Nmr equation. This states that the frequency of precision, this is what I told you, precision is directly proportional to the product of the magnetic field strength, because it is dependent on the magnetic field strength and the gyromagnetic ratio. Gyromagnetic ratio is specific to specific nucleus. Carbon has got one gyromagnetic ratio, and proton has got a different gyromagnetic ratio, specific to different magnetic nuclei. So the precisional frequency is dependent on what? It is dependent on the magnetic field strength that is applied and the gyromagnetic ratio of the nucleus under study. So this is stated mathematically as this is omega is equal to GB0. GB0 is G is the gyromagnetic ratio, B0 is the applied magnetic field, and this is the precision frequency. So that is the principle of C13 Nmr. I have not gone into very much detail because it is just same as Proton Nmr. That's the reason why I have just given you a brief introduction about that principle of Proton Nmr. Now, we are going to see various types of C13 Nmr spectra. There are mainly 4 types of C13 Nmr spectra. One is undecoupled spectra, broadband decoupled or proton decoupled spectra, and off-resonance decoupled spectra, and selective proton decoupled spectra. So we'll be discussing each of them separately in detail. What is undecoupled spectra? What do you mean by undecoupled spectra? The name itself suggests nothing is decoupled here. Actually, I should tell you that carbon, you must have seen coupling, spin-spin coupling in Proton Nmr. So similarly, carbon also undergoes extensive coupling. And in this type of spectra, all carbons between carbon, so when coupling occurs, then there are magnetic nuclei in the neighborhood, in the vicinity, is it not? For example, in Proton Nmr, neighboring protons, neighboring non-equivalent protons couple undergo spin-spin coupling. Similarly, carbon also undergoes coupling with attached hydrogens. Carbons can undergo coupling with attached carbon. I mean, CC in C13 in the attached carbon in the framework, and second carbon, third carbon, fourth carbon, etc. All these couplings are observed. In undecoupled spectra, we are not decoupling anything. Therefore, we'll be getting all the couplings between carbon and hydrogen and other magnetic nuclei present in the molecule. What are the other magnetic nuclei? Other than hydrogen, fluorine may be present, phosphorus may be present, boron may be present, which are magnetic. They will also undergo coupling if we record undecoupled spectra, undecoupled C13 Nmr spectra. And I told you carbon undergoes extensive coupling with not only attached hydrogen and hydrogens. It will also couple with hydrogens which are 2 or 3 bonds away, and even sometimes longer range couplings if the distance between that carbon and that hydrogen, because of the 3-dimensional network, if they are in the vicinity, even longer range coupling is also possible. So this results, because too many couplings means too many signals, too many splitting patterns. Therefore, it results in very complex spectra, even for simple molecules. Therefore, very difficult to interpret. And that is the reason why undecoupled spectra are not normally used. Okay. And so I'm just showing you how, what type of coupling, how it can be coupled, what are the couplings that can be observed. For simple molecule, propanol, I've just taken propanol. You see, I'm just observing the signal of this carbon which is attached to OH. Okay, this can undergo coupling with the attached hydrogens, CH2. Okay, this is known as J1 coupling. This can couple with the hydrogens which are on the second carbon. This is J2CH coupling, and they can this carbon can couple with the CH3 protons also. We call it J3 coupling. So J1CH is observed, J2CH is observed, J3CH is observed. So all J1, J2, J3, CH couplings only I am talking about, not CC coupling. Because why CC coupling is not, I'm not talking, because the probability of finding two C13s in the attached positions is very, very, very rare. That also you will know in couplings in detail. Okay. So I am just showing you the coupling between carbon and hydrogens, directly attached hydrogens, and which are on the second carbon, attached carbon, that is second carbon, and which are on the third carbon. So see, if you observe in three couplings, the couplings between carbon and hydrogen, which are 3 bonds away. Sometimes even J4 coupling, J5 coupling also can be observed. I'm just showing you up to J3 coupling. Even then, you see, J1, J2, J3 couplings are possible. And it will give you, see, theoretically 36 lines are possible for CH2OH carbon in one propanol. See, you know that rule 2NAI plus 1 into 2NBI plus 1 into 2NCI plus 1. That rule which you have studied in Proton Nmr is applicable here also. So you 2NAI plus 1 means A type of protons, 2 into 2, that I is a splitting pattern, that is spin number, I is equal to R for hydrogen. Okay, so 2NAI plus 1 plus 1, I is half here, you calculate. And now 2NB, what is NB? B is 2, B type of protons, that is, these are NB, so B 2 protons. 2NBI plus means 2 into 2 into half plus 1. 2NCI plus 1, so C type of protons are 3. 2 into 3 into half plus 1. Okay, so that comes to total. If you calculate, it will be 36 lines. 36 lines are possible for CH2 carbon only. CH2 carbon only. And for that simple molecule. So 36 lines for this carbon. And for this carbon also again, these two it can couple, and these two it can couple. These 3 it can couple. So that means 2Na plus 1 into 2NBI plus 1 into 2NCI plus 1. So here, that also 36 lines. So since all the spin couplings are observed, these spectra are called non-decoupled or undecoupled spectra. Understood? Propanol, a very simple molecule. I'm just showing you the coupling of CH2 carbon with CH2OH, this carbon which is attached to OH. So how many lines it is giving? 36 lines it is giving. Similarly, other carbons also give more number of lines depending on the number of hydrogens attached. And I'm just showing you up to J3 coupling. And even sometimes J4 couplings also observable. So that's the reason why it gives you a complex spectra. Let's see. The undecoupled spectrum of propanol. Continue this right here. J1, J2, J3 couplings are possible. Theoretically, 36 lines are possible for CH2OH carbon in propanol. Okay. Since all the spin couplings are observed, these spectra are called undecoupled spectra. The undecoupled spectra of even simple molecules. Propanol is a very simple molecule. So it's also complex. Why? Because due to overlapping multiplets. 36 lines for this carbon, 36 lines for other carbon, and 36 lines for other carbon. Definitely there will be overlapping. Okay. And another problem here is the coupling constants are of C13H are frequently larger than the chemical shift differences. They are between 125 up to 125 to 250 hertz. So they are more. So sometimes the signals of the split lines will be very widely separated. We will not be able to differentiate between the chemical shift or the split signal. It's very difficult. It becomes very difficult when you. That is the reason why undecoupled spectra are not normally used. And what are very important? The important are broadband decoupled spectra and SFORD. Okay, so broadband decoupled spectra. Here, broadband decoupled spectra. The name itself suggests something is decoupled here. Okay. So what is decoupled? What are decoupled here? All the protons present in the organic molecules, the sample are decoupled, whatever we are dealing with. Okay. So broadband is the band of radio frequencies corresponding to the protons present in the organic molecules. So see here, why they are necessary? As I told you already, the coupling constant between carbon and directly attached hydrogens ranges from 125 to 300 Hertz. So since this results in overlapping, proton decoupled spectra are used. So this broadband corresponds to broadband of radio frequencies consisting of all the protons present in a molecule. Okay, so that is what is written here. In this technique, what is done? Simultaneous irradiation of all the proton resonances. All the proton resonances is carried out with a broadband generator while observing the carbon frequencies. So in organic molecules, let us just assume that we have only carbon and hydrogen. How many types of magnetic nuclei are there? Carbon is there, hydrogens are there. So since coupling can be observed in undecoupled spectra, there will be coupling between carbon and attached hydrogens, and the hydrogens present on the second carbon, the hydrogens present on the third carbon, and sometimes fourth carbon. So that results in complex spectra, as I already told you. So here, what is being done here? How the complexity is arising? The complexity is arising because of the coupling between carbon and various hydrogens present in the molecule. And if we can remove that complexity, that means if we decouple all the protons present in the molecule, then the spectrum will be simplified. And that is what is done here. Here, what is done? Simultaneous irradiation of all the proton resonances. Simultaneously, all the protons are irradiated. So that means all the protons will be flipping from low energy state to higher energy state very fast, because here we are not giving any time for them to relax. So they are going faster transitions from lower energy state to higher energy state, lower energy state to higher energy state, lower energy state to higher energy state. That is the reason why carbon, the attached carbon, will not be able to see whether the hydrogen is present in lower energy state or whether it is present in upper energy state. Actually, this spin, see, when you are, so you need to again go back to your proton NMR spectrum here. How you get a doublet? How you get a doublet? When carbon is attached to one hydrogen. When one carbon is attached to, when one type of hydrogens are attached to another type of hydrogens, the one type of hydrogen, one set of hydrogens see the other hydrogen in two spin states. One is in lower energy state, that is in line with the magnetic field, and the other one is higher energy state. That means in lower energy state it can see, in higher energy state it can see. So here in lower energy state, it is the magnetic moment has become little higher for this set of hydrogens. In opposite state, the magnetic moment has become little low. So that is the reason why you will get a doublet signal. Means one is slightly upfield than the original position, one is slightly downfield than the original position. That means two signals you are getting. Why? Because the set of protons are able to see the other set, other neighboring set in two spin states, in line, opposite in line. That is what is removed here. So here, carbon, when it is attached to hydrogen, it can also give you a doublet, but it is not giving you a doublet. Why? Because those protons are simultaneously radiated with the proton frequency range corresponding to all the protons present in the molecule. So then what happens? The carbon is not able to see the attached hydrogens in different spin states. It can see only the average spin state. That is the reason why it is decoupled. Only carbon signal is observed, it will not undergo any splitting. Okay, this results in decoupling of all the protons. And the intensity of the signals also increases due to NOE, nuclear over-Hauser effect. Okay, so that is the reason why in proton decoupled spectra, the coupling due to hydrogens is not observed, and all carbons, different non-equivalent carbons, will give you different signals. So the spectrum is super simplified, very simple it becomes. So the number of signals gives the number of different types of carbons in the molecule. For example, you are taking ethanol. Ethanol, how many carbons are there? 2 carbons are there. Now, these 2 carbons, CH3 carbon and CH2 carbon. So you will get 2 signals. You take propanol. How many signals you will get? 3 signals you will get, because you have 3 non-equivalent carbons. CH3 is there, CH2 is there, and CH2 is there. So you will get 3 signals. So like that, number of signals gives you the number of different types of, that is, non-equivalent carbons present in the molecule. So the number of signals is equal to the number of non-equivalent carbons present in the molecule. And C13 NMR signals are not integrated. This is the difference between proton NMR and C13 NMR, C13 signal. In proton NMR, proton signals are integrated. Actually, the area under the integration is proportional to the number of hydrogens present in that signal, corresponding to that signal. Whereas in C13 NMR, signals are not integrated. It will not give you the, the intensity of the signal will not be proportional to the number of carbons in that state, okay, in that magnetic environment. So therefore, the peak intensity is not proportional to the number of absorbing carbons. Okay, the intensity increases due to nuclear over-Hauser effectively. See, I am just showing you one example. So some examples here. Just dimethyl ether. Here, only one type of carbon is there. Therefore, only one signal. Chloroethane. How many carbons are there? 1, 2. One CH3 carbon, the other CH2 carbon. 2 signals you get. And in methyl acetate, how many carbons are there? How many non-equivalent carbons are there? One CH3 carbon, one carbon, this ester carbon, carbonyl carbon, and the OCH3 carbon. So again, you get 3 signals. In broadband decoupled spectra, the number of signals is equal to the number of non-equivalent carbons. And there are some more examples for your reference. See, ethane. Ethane, both carbons are equal only. Therefore, only one signal is observed. Propane. How many non-equivalent carbons? This one, this, another one. This and this are same. Okay. So, 2 signals are obtained. Here, pentane. This is different. This is different, and this is different. And these 2 are same. These 2 are same. So, 3 non-equivalent carbons. Therefore, 3 signals. Similarly, methyl ethyl ether. 3 non-equivalent carbons. 1, 2, 3. So 3 non-equivalent carbons, therefore 3 signals. Benzene, you see, 6 carbons are there, but all are equal. Therefore, only 1 signal. Some more examples. Here, ethoxybenzene. All benzene carbons are not. Here you see, this is 1 carbon, non-equivalent carbon, CH3 carbon. This is another carbon, non-equivalent carbon, CH2 carbon. And in benzene ring, see, this is another ipso carbon, which is attached to oxygen. It's different. And these 2 are same. Ortho to ethoxy group. This and this are same. So 1, 2, 3, and this 4. And this meta also same, 2. And this is para. So 2 orthocarbons, 2 metacarbons, and 1 paracarbon. So 1, 2, 3, and 1 ipso carbon. So 4 aromatic signals and 5 6 signals, 6 non-equivalent carbons, and therefore 6 signals. Here you see how many non-equivalent carbons are there. This is 1, this is 2, and carbon, this ester carbon and ipso carbon. This 1, 2, 3, 4, 5. See, why 5? Though there are more number of carbons, because there is symmetry. Plane of symmetry is there. See, they are same. This and this are same. These two and these two are same. And that's all. This carbonyl and this carbonyl are same. This CH2 and this CH2 are same. This methyl and this methyl are same. So overall, 1, 2, 3, 4, 5. So 5 non-equivalent carbons. Therefore, 5 signals. So that is about broadband decoupled or proton decoupled. We also call it proton decoupled. So just let us revise. What is that we have seen? In proton decoupled spectra, all the protons present in the molecules are decoupled. All the protons, when we say all the protons, all these protons, CH2 protons, these aromatic protons and other protons. So in the organic world, whatever you are dealing with, whatever sample you are doing, whatever structure you are looking at, the protons are, all the protons present in that molecule are decoupled. So you will be able to see only carbons. So that means that the couplings will, due to carbon and hydrogen, will not be observed. So the number of signals will be equivalent to number of non-equivalent carbons present in the molecule. If there is symmetry, okay, if there is symmetry, there will be less number of signals. For example, there is symmetry here. Here though 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons are there. But still, you are getting 5 signals only. Why? Because there is plane of symmetry here. So that's the reason why when there is no symmetry, the number of carbons, let us take heptanol. Heptanol, is there any symmetry? There's no symmetry. So how many signals do you expect? You expect 7 signals. Next is off-resonance decoupled spectra. Off-resonance decoupled spectra. See, in undecoupled spectra, there is one disadvantage. What is the disadvantage? All the couplings are observed. Therefore, complex spectra are obtained. In completely decoupled, that is broadband decoupled, completely decoupled, or proton decoupled, all are same only. In completely decoupled spectra, what we have seen, we have lost all the couplings due to carbon and hydrogen. So the spectra are simplified, no doubt, but you will be losing the information about the coupling information between carbon and hydrogen. So you will not be able to identify which is CH3 signal, which is CH2 signal, which is CH signal, which is quaternary carbon signal. So some of the information is lost there. So that disadvantage. So what is the disadvantage in broadband decoupled spectra? The disadvantage of proton decoupled spectra is the coupling information is lost. Okay. So whereas proton coupled spectra give complex spectra. So this is one disadvantage here. This is another disadvantage here. That is overcome in off-resonance decoupled spectra. How? In off-resonance decoupled spectra, they give both coupling information and also it will simplify the spectra. How? Here, only coupling due to attached hydrogens is observed. The coupling due to attached hydrogens is observed. And all that is J1 coupling is observed. And J2, J3, J4 coupling is not observed. So that is the reason why coupling information is retained and spectra will be simplified. And how it is achieved? It is achieved by irradiating the sample. Here also we are doing some decoupling, but it is not, the resonance frequency with which we are decoupling does not fall completely in the proton frequency range. It is slightly off resonance. Slightly off resonance means not completely in the proton range, slightly upfield. See, 1000 to 2000 hertz upfield from TMS, or 2000 to 3000 downfield of proton frequency. It's not just, it's approximate, little slightly, and this side slightly, the other side also may be there. This time showing you the range. So in the proton range, that is 1000, 0 to 1000 or 1200 range, the frequency is not, that radio frequency is not used. Corresponding to proton frequencies, that radio frequency is not used. Which is used off resonance. That means slightly away, slightly closer to the proton frequency range. Not the exact proton frequency range, it is closer to the proton frequency range. Slightly off resonance, that is either off field from the TMS or 2000 to 3000 downfield of proton frequency of TMS is used. So what happens when we use this, that resulting spectrum will not have J2, J3, J4 couplings. Other long range couplings are lost here. Only the coupling due to the carbon and that attached hydrogen is observed. And that also is not completely observed. Only residual coupling information is observed. That means the distance between the coupled, that multiplets, is not equal to the coupling constant. It's only residual. I told you the coupling constant range between 125 to 250 hertz. So that is that wide distance between the spread signal is not observed in this day, because again that will come into the spectrum. So here only residual coupling, small coupling will be observed. So the spectrum just looks like proton NMR multiplets, like triplet, doublet, quartet, etc. They look like simple proton NMR spectrum, but here we will be observing carbon signals only. So that coupling constant also given by this equation, J residual 2 by J delta nu by gamma B2. Gamma B is applied multiple, log magnetic ratio, and this the frequency differences. So J is the true coupling constant, normal spin coupling constant without any decoupling, and delta nu is the difference between the resonance frequency of the protons of interest and the decoupler frequency, and gamma is the gyromagnetic ratio of the protons. So this is the the strength of B2 is the strength of the rotating magnet in the decoupler frequency. That is the decoupler frequency, proton frequency which we are using, that will also generate magnetic field. So that is the magnetic rotating magnetic field, the decoupler frequency. So this residual coupling is proportional to the J1 coupling, J1 CH coupling. The power of the decoupling and the distance at which the decoupler frequency is set from the protons being decoupled. So this is dependent on these factors. So in off resonance decoupled spectrum, then what we can expect, only carbons, only hydrogens attached to carbon coupling is observed. Carbon directly attached to hydrogens coupling is observed. So that means, based on the Na+1 rule, that is normal spin splitting rule, coupling rule, what is that you get? CH3 carbon. Since you have three hydrogens to Na+1. So 3 hydrogens, 3 into 2 Na+1, 2 into 3 into half plus 1. That is 6, similar to N+1. Okay. So 3 plus 1. Quartet. All CH3 carbons appear as quartet. So all CH2 carbons appear as triplets. All CH carbons appear as doublets. So all quaternary carbons appear as singlets. So what is the advantage here? What is our advantage here? In SF4, that is off resonance decoupled spectrum. What is that you get? You will be able to identify which is CH3, which is CH2, which is CH, and which is quaternary carbon. Signals different carbons in the structure, in the molecule. So that is that. Examples I'm just showing you. Ethyl acetate, C. Off resonance decoupled C, that in the mass spectrum of ethyl acetate gives. How many signals? How many non-equivalent protons are there here? One non-equivalent carbons. 1, 2, 3, 4. 4 non-equivalent carbons are there. So you will get 4 signals. Here CH3. How many quartets you will get here? 1, 2 CH3s are there. So this CH3s will give you a quartet. And this CH2, it will give you triplet. Oh, and this OCH2, that H2 is missing. OCH2, that is a triplet. and this is carbonyl carbon. Though it is not attached to any proton, because it is a carbon spectrum we are observing, this will give you a singlet. Carbonyl carbon of this ester will give you a singlet. And this is to the body. So in ethyl benzoate, how many signals you expect? How many non-equivalent carbons are there? 1, CH3, CH2, carbonyl carbon, and this is carbon. And these two are same. These two are same. This is an. So overall 1, 2, 3, 4, 5, 6, 7. 7 carbons. 7 non-equivalent carbons are there. So you get 7 signals. So again CH3 quartet. This is the CH2 CH2 triplet, and this is singlet. And ipso, it will be also a singlet because it is not attached to any hydrogen. And this ortho carbon will be a doublet because it is attached to one hydrogen. Metacarbon also a doublet, and paracarbon also is a doublet. So overall 7 signals you get, in which 1 quartet, 1 triplet, and 2 singlets, and 3 doublets. Okay. More examples. Ethyl methyl ketone. See, how many non-equivalent carbons are there? 1, 2, 3, 4 non-equivalent carbons are there. So 4 signals. So off resonance decoupled spectrum gives you 1 quartet here, another quartet here. So 2 quartets, 1 triplet, CH2 triplet, and this is a singlet. So 2 quartets, 1 triplet, and 1 singlet. Okay. And this is ethyl protonate, protonic acid ethyl ester. So here how many carbons are there? All carbons are non-equivalent over here. Say 1, 2, CH2 carbon, CH2. This ethyl ethoxy group 1, CH3, CH2, and this ester carbon, and double bonded alkene carbons 1, 2, and so 2 CHs are there. So you get 2 quartets, and 2 CHs are there. So you get 2 doublets, and 1 carbon ester carbon is there. That is 1 singlet. Okay, and 1 more CH2 is there. That is a triplet. Okay, so that is. So that is about off resonance decoupled spectra. So let us just revise. In off resonance decoupled spectra, what is that we are doing? What is that is being done? So all long range couplings are removed. Only the coupling due to attached hydrogens is retained. So only coupling due to attached hydrogens is observed. That means CH3, CH2, CH. You will be observing. Okay. And J2, J3, J4 couplings are removed. How they are removed? By making use of a frequency which is slightly off resonance than the normal proton radio frequency range. So that will give you a simplified spectrum, and also it will retain the coupling information. So this is very useful. Then third one is selective proton decoupling. Selective proton decoupling technique. In this selective proton decoupling technique, you know that name again itself suggests protons are selected and they are selectively decoupled. So this is similar to double resonance technique which you have studied in first year in Proton Nmr Spectroscopy. What is that double resonance? When you have 2 hydrogens, adjacent hydrogens, non-equivalent hydrogens are there, which are undergoing coupling, which undergo spin-spin coupling. What is done in double resonance? One set of protons is doubly radiated. One set of protons is doubly radiated. Not only general proton frequency, another selected proton radio frequency which corresponds to that proton set is used, and that double irradiation results in faster excitation and relaxation of that particular protons which are being doubly radiated, and the adjacent proton will not be able to see the different spin environment. So it will be able to see only the average spin of the neighboring nucleus. That is the reason why it will not be coupled. It will not undergo coupling. So suppose if you have ethanol, if CH2 protons are doubly radiated, normal ethanol spectrum, CH2 is a quartet and CH3 is a triplet. Like, okay, methyl ethyl ether, let us say. In methyl ethyl ether, OCH3 is a singlet and CH2O is a quartet and CH3 is a triplet, is it not? So if you irradiate CH2 protons there, what happens? CH3 will not be able to see CH2 protons in different spin orientations, spin environment, okay? Therefore, CH3 signal will be converted to singlet. So that is double resonance. That is simply, we don't use double resonance technique for methyl ethyl ether, but just to explain you, I have taken that simple example. So what is that? What is happening there? When you double irradiate, when you irradiate one specific proton set, what is happening? The protons that are adjacent to it are being decoupled. So the spectrum will be simplified. So the same thing we are doing here. Only thing is here we are decoupling protons and we are observing carbon signal. So in this technique, a specific proton resonance is identified and this is used for decoupling. And this is similar to double resonance technique in proton NMR spectroscopy. So in this selective proton decoupling technique, the sample is irradiated with low radio frequency. So it is used to simplify the NMR spectrum. It's very useful to determine which spin multipliers are actually linked to one another. So if I take an example, is well. So, example, ethyl protonate, ethyl protonate, and the another one is propyl 4-methoxy propyl benzoate. Propyl 4-methoxy benzoate. Okay, here let us see. In 4-methoxy propyl 4-methoxy benzoate, how many signals you can observe? How many non-equivalent carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 signals can be expected. So here you see one OCH3. This is a quartet. And this OCH2 will be a triplet. See, since this CH3 is attached to oxygen, this CH2 also is attached to oxygen. They will be closely spaced. There may be overlap. OCH2 carbon and OCH3 carbon may overlap. So this quartet and this triplet may overlap. So how do we know which signal corresponds to which carbon? By way of selective proton decoupling. How? Suppose if you take this CH2 proton frequency and doubly irradiate it. So what happens? These CH2 protons only these CH2 protons are decoupled and all other coupling information is retained. So only this OCH2 carbon will appear as singlet. Instead of triplet, it appears as singlet. Whereas this will appear as triplet, this will appear as quartet, this will appear as quartet, and the rest all is to anyway, they are not attached to protons, so there is no decoupling, no coupling. And this will appear as doublet, this will appear as doublet. So what is the information we are getting here? By doubly irradiating these OCH2 protons, what is happening? The carbon that are attached to this particular proton is decoupled. Okay, that protons are decoupled. So that particular carbon appears as a singlet. Rest all coupling information is retained. So we know that particular signal which is giving rise to that triplet is the signal into this OCH2 carbon. So even in that quartet we can identify then once it is decoupled. Similarly, we can decouple this also. Any other set also, but I've just shown you this because it is easy to identify the resonating frequency of this OCH2 protons and selecting that radio frequency, we can decouple those protons, and you can simplify the spectrum. Here also you see. Similarly, off resonance decoupled spectrum of ethyl protein shows two quartets, two doublets, two quartets, two doublets, and triples. After decoupling OCH to protons. Suppose if you decouple this OCH to protons, how the spectrum will look like? This CH3 appears as a quartet, this CH3 appears as a quartet. Two doublets, two quartets, and two singlets will get. This also will become a singlet. This will be a singlet, this will be a singlet. That is selective proton decoupling. It is useful especially when there are overlapping signals in the molecule. Then chemical shift. So we have seen chemical shift. We have learned about chemical shift. We have learned about chemical shift in proton NMR. So what is chemical shift? The name itself suggests again, it is a shift. So it is a shift in the position of an absorption nucleus with a reference nucleus. It's called chemical shift. Actually, we call it chemical shift because it is dependent on the chemical and magnetic environment. This shift is dependent on chemical and magnetic environment of the nucleus. That is the reason why we call it chemical shift. So it is simply, broadly speaking, it is a shift in the position of an absorption nucleus with a reference nucleus is called chemical shift. So what is the reference used in proton NMR? EMS, tetramethyl silane. So here also we use tetramethyl silane. So again here in proton NMR, we have seen all chemically equivalent protons will have same chemical shift, and chemically non-equivalent protons have got different chemical shifts. So here also same thing. Chemically equivalent carbons have same chemical shifts, whereas chemically non-equivalent carbons have different chemical shifts. Since they have different chemical shifts, they will appear at different places. So they as signals. That is the reason why chemically non-equivalent carbons will appear as different signals. Okay. In C13 NMR, these signals do not overlap because the chemical shift range is quite wide, between 0 to 240 ppm. Sometimes it may go beyond 240 ppm, so like more downfield than TMS, like very positive carbons, like carbonyl, carbocations, etc. And they can be upfield also to 0, like carbanions and highly shielded carbons. They may be more than, upfield than TMS also. But normal range is 0 to 240 ppm. So that is what is a chemical shift? Shift in the position of the signal from the reference signal. What is the reference signal used? It is the TMS. Yes, just general range of chemical shift table I have given you. Just see if you have a type of carbon, the CH3 carbon, which is attached to R, anywhere between 0 to 35. It's approximate range only, slightly beside that side will be there. See, this secondary carbon, primary carbon this way. The secondary carbon is 15 to 55, slightly more. The tertiary carbon, again 25 to 55, 60. And a quaternary is more, 30 to 40. A halogen attached, halogen or nitrogen attached, between 10 and 65. It varies, okay. Oxygen attached, this is the range. Generally, it appears between 50 and 60. Sometimes, in rare cases, up to 90. So 50 to 60 is normal, but up to 90 also. Some specific molecules you may come across. And alkynes 70 to 90. Alkenes 80 to 150. Actually, it's around 120. But depending on the substitution that are, it may vary between 80 and 150. So in factors affecting chemical shift, I'll tell you what are the factors that will affect the normal range, from normal range to lower or higher range, downfield or upfield range. With benzene, you see around 120. Actually, benzene is 128, but it can go upfield than 128 and it can be downfield than 128. Anywhere between 110 and 170. That also depends on the substitution only. And it's ester carbonates. See, ester carbonate 165 and 175. Carbonic acid, carbon 175 to 185. Aldehyde 119 to 200. See ketone 200 to 220. You can differentiate between carbonyl carbon and aldehyde carbon. And actually, ketonic carbon and aldehyde carbon. In fact, you can get the differentiation from proton NMR also, because proton NMR aldehyde equivalent and ketone equivalent. So that is a normal range of chemical shift. You need to remember them approximate ranges. Chemical shift equivalence. What is chemical shift equivalence? The carbons in a given molecule are interchangeable by symmetry operation or a rapid rotation. They are said to be chemically equivalent. So, if they are interchangeable by symmetry operation, you know the symmetry, and symmetry operation or rapid process. For example, ethane. Two carbons are same. Two types of carbons. Here you see tertiary butanol. This is primary carbon, quaternary carbon. In here, para-xylene, 1,4-dimethyl-benzene. So how many carbons are there? Here there is symmetry. So plane of symmetry, 1, 2, 3 types of carbons. Here you see any symmetry is there? No symmetry, because one side CH4 is there, other side OM is there. So they are different groups. So there is no symmetry. So all carbons are different. 1, 2, 3, 4, 5, 6. So 6 carbons, therefore 6 moles are obtained. And so when they are equal, yeah, this one. This is the here again. I told you here there is symmetry. 1, 2, 3, only 3. No, 3 actually. Here even these two are same. These two are all 4 are same. Yeah. So that is so chemical shift equivalence means when there is symmetry, you will get less number of signals than the carbons present in the molecule. So you can approximately calculate the chemical shifts also here by making use of a simple equation. You will just since the time is up, I just within 1 minute I'll end. In the next class I'll continue this calculation of chemical shifts. So and just revise whatever we have learned today. What is the significance? Significance of C13 NMR is direct observation, because many natural products contain more number of carbons and complex carbon framework, which you can observe directly. And in the complex natural products, proton NMRs are very complex, therefore very difficult to interpret. Therefore, C13 NMR will be very useful for structural investigation. At disadvantages of C13 NMR, low abundance, low magnetic moment, therefore less sensitivity. You need more sample to record the spectra. And what is another disadvantage? Extensive coupling. So because of this coupling, you need to do decoupling experiments. So, however, we have a technique which can give you that coupling information, that is SFORD, single frequency off resonance decoupled spectrum, or off resonance decoupled spectrum, where only the coupling information between carbon and hydrogen is observed. And chemical shift equivalence means the carbons which are not equivalent, which are not interchangeable by a symmetry operation or rapid rotation. They are said to be non-equivalent. We have 4 types of spectra. Undecoupled spectra, all coupling information is written. And for broadband decoupled spectra or proton decoupled spectra, here only the coupling information is not written. All the coupling information due to all hydrogens is lost. So all carbons are paired as singlets. And in off resonance decoupled spectra, in off resonance decoupled spectra, only the coupling due to carbon and hydrogen is written, and all other coupling information is lost. And here you must one more point I just forgot to tell you. Here broadband decoupled spectra, only all the proton coupling is lost. But if you have other magnetic nuclei such as fluorine and P31, that coupling information will be written. Anyway, we'll know more about it later. And selective proton decoupling, we are decoupling, we are selecting a proton, particular proton, and using that specific proton frequency as decoupling frequency, so that that particular proton is decoupled and all other coupling information is retained. So that is selective proton decoupling. And the chemical shift is shift in the absorption position of the nucleus, that is here carbon from the reference nucleus, TMS. So that TMS is the reference here. So you can calculate, just show you, you can calculate the chemical shifts of alkanes by making use of these equations. Delta of any particular carbon under consideration, the chemical shift of the particular carbon, you can calculate by this equation, minus 2.5 plus summation of Na. N is the number of, A is the additive shift parameter, N is the number of that particular additive shift parameter. For example, is a, what is negative minus 2.5 here? It is a shift, not shift. It is a shift for methane. Shift. It is a shift of methane. And A is the additive shift parameter. N is the number of carbons for each shift parameter, whichever is contributed. Now, here is this table. Actually, you should remember this table. A small table and very difficult. It's not very difficult to remember. See, a carbon 13 atom under consideration. When you have one alpha carbon, additive shift parameter is 9.1. If you have 2 alpha carbons, it will be 2 times 9.1. Beta carbon 9.4, gamma carbon minus 2.5, delta carbon plus 0.8, epsilon carbon 0.1. And if it is a primary carbon attached to tertiary carbon, minus 1.1. If it is a primary carbon attached to quaternary carbon, it is minus 3.4. If it is a secondary carbon attached to tertiary carbon, it is minus 2.5. If it is secondary carbon attached to quaternary carbon, it is minus 7.2. If it is tertiary carbon attached to secondary carbon, it is 3.7. And if it is tertiary carbon attached to another tertiary carbon, it is minus 9.5. It is quaternary carbon attached to primary carbon, minus 1.5. It is quaternary carbon attached to secondary carbon, it is 1.4. So these are the parameter values. If you have to incorporate in this equation to get the calculated chemical shift of that particular carbon under consideration. So we will do some calculations in the next class. So with this, I just close this lecture. If you have any doubts, you can mail or message. You can take the mail ID or Mr. Bodhishara. You can discuss if you have any doubts here. Okay. Thank you. Thank you for watching.
మేడం ఎగ్జిట్ కావచ్చు, రేపు మళ్ళీ కంటిన్యూ చేయొచ్చు.
అదే
సరే,
ఓకే.
ఓకే.